everybody. Our first talk today is by Davide Lanti, and he's going to talk about OBDA, constraints for effective query answering.
So, thank you very much. So, I am Davide Lanti, a co-author of this work about ontology-based data access, for constraints on ontology-based data access systems. And, okay. So this talk, we have an introduction because maybe not all of you is familiar with ontology-based data access. And then we will say what is the main problem in the field of research for ontology-based data access, which is the performance problem. And then we will move to the solution proposed with this work. And finally, we conclude with an evaluation. So if I find the right button. So this is the first sentence I found in publications about ontology-based data access, which is essentially the problem of accessing a set of existing data sources by means of a conceptual representation expressed in terms of an ontology. So here the key word is accessing, and the existing data source is important as well. So this is more or less a picture of what it is. So you have a user that issues queries to a semantic representation of the data stored in a database. And this conceptual view is realized by means of mappings which relate the predicates in the ontology to queries over this database system. So what would happen is that in the database we have some content, and then by these mapping assertions, by for instance executing this query, we will get these triples in the RDF graph. And here another keyword is the fact that this graph is virtual, because ontology-based data access is the problem of accessing a data source, not about copying a data source into a virtual RDF graph. So how this is done, how can we keep the thing virtual? This is achieved by essentially rewriting the query. So you have an initial Spark query. For instance, we want to have all the elements of type B. And then through rewriting, we include the knowledge that is incorporated into ontology into the query. So that here says that every element of A must be also an element of B. And therefore, if I want all the B's, I also have to look for the A's. But this is not yet a query over the original database. This is just a query over the virtual RDF graph. So the unfolding step translates this into an SQL query that then will be evaluated over the database, will return some results, and this result will be translated into a result for the original Spark query. Because remember that the Spark query, for instance, individuals of classes are URIs, but in the database there are values. So, for instance, here ID is just a value to the rewritten query that are entailed by the virtual RDF graph alone, so we discard the ontology part. So this would be the rewriting step. And then finally, this is just correspond to finding all the SQL results to an evaluation of the unfolding of the rewritten query. So you see here there are two translation steps of the input query, so you might expect that this translation come with a cost. The first cost is, of course, the fact that you have a limitation on the ontology language that you can use. So for ontology-based data access, you can use just up to R2QL ontologies. So you have like disjointness, subclasses, and inverse properties, not much more. And but another problem, more subtle, is really about the performance, also with these ontologies. So the first result for 2012 is that when you do rewriting, you cannot avoid an exponential blow-up in the size of the rewriting. This is the worst case, of course. And the same holds for the unfolded queries. So once you rewrite, you get a blow-up, and once you unfold, you get again another blow-up. So now we arise the question, well, is OBDA meaningful? I mean, does it make any sense in practice? The answer is yes, because these are essentially just worst-case analysis, and the next two techniques I'm going to show will allow OBDA to work in practice, at least prior to this publication. So the first idea was to avoid the rewriting by compiling the ontology T into the mappings. So this problem that I want to find all the answers that are entailed by the virtual RDF graph for the rewriting becomes the problem of finding all the answers just for the original query. and replacing this virtual RDF graph with the saturation, where is the graph realized with the initial database and a mapping which is called the T-mapping that incorporates the ontology. So here again our example, we have an ontology mapping, and it's essentially you just take the query that gives OBDAs, you take the way on how you construct the individuals, and you add that as a mapping for B. So the saturation, of course, does not always work here. I said I avoid the rewriting, but of course, if you have conjunctive queries, which is not in this setting, but you have existentials in the query, then this is not enough. You still need a rewriting, even though a limited form of rewriting. But here we are dealing with SparkQuery query, and SparkQuery does not have existentials, so this is sufficient. Now, this technique works well because it works in combination with this technique, which is essentially comes from the semantic query optimization for databases, which is removal of redundant unions or redundant self-joins. So you use the primary inferring key from the database schema, and then you change this problem of finding the evaluation into finding all the answers, so the evaluation, but you know that the database satisfied integrity constraints. So you want to find this query optimized, which of course has to be easier to execute than the query unfold. So this is the use case I'm going to present today. This is Statoil use case. My colleagues work in the context of the Optic project, which is a European project where they try to investigate whether ontology-based data access can be used in real-world scenarios. And Statoil, which is the Norwegian oil company, provided one use case for OBDA in their company. So this is kind of a lower bound. They provided this OBDA setting with queries, ontology, and mappings, and a database, of course, so that you have the whole input for the OBDA system, and they want all these queries to be answered, at least to say, okay, at least this might be useful for us, because these queries are queries that they cannot currently run with their, that they cannot easily formulate, actually, by means of their tools that they currently have. So OBDA would formulate these queries for them automatically, but still it remains the question whether, okay, you formulate the queries, but do the query execute well? I mean, is this formulation efficient? The OBDA system, and we test this on top, because on top is a state-of-the-art OBDA system, which is the main OBDA system we used in this Optic project. So, with the optimization I discussed so far, we have 17 timeouts, which is not acceptable, because this is a lower bound on the applicability of OBDA in the Statoil use case. So essentially, on top failed on the Statoil use case. So why did it fail? I mean, the engineers that gave us the query, they said that essentially this query is difficult for them to formulate, but they can still formulate them, and expect that these queries can be executed. So what was happening instead is that the data storage expert, while formulating the query, uses some knowledge which is not available to the OBDA system. Because if you remember, I just produced, the OBDA system produces rewriting and unfoldings that are entailed by this object. But if you have an external component, like a constraints, then, of course, you can simplify with respect to constraints, but you will not obtain some complete rewritings and unfolding with respect to this. But this is what we are doing here. We are giving the domain experts a way to define these constraints, to make the OBDA system aware of these constraints. So the problem would become essentially to find all the entails answers from the RDF graph and the ontology, but under the assumption that this OBDA instance satisfies the constraints. And here we investigate two kinds of constraints, exact mappings and virtual functional dependency. So in exact mapping, essentially we have a predicate which is defining the mapping, but for which a mapping is which is a subset of the input mapping, but this mapping is enough to retrieve all the elements for this predicate. So essentially the idea is that if you replace in the input mapping all these submappings for all the predicates, then you will get the same saturation of the virtual RDF graph. So in turn, you will get, of course, the same results because when evaluating the queries, because of course OBDA is sound and complete in the end. The unfolding is sound and complete. So the idea is the following: use this exact mapping notion to reduce the T-mapping. So when you do the T-mapping, if you remember the example, I was expanding the initial set of mappings. So exact mappings will just say, look, for this term, do not do the expansion. So this is why you will get a smaller set of mappings. And of course, if you have fewer mappings, then you will have a shorter unfolding, because you do not have to consider all the possibilities there when you do the union, as I showed before. But I have an example after, actually. The second more involved constraint is virtual functional dependencies. So I start first from an example. So a virtual functional dependency is an expression where you have on the left-hand side a template and a placeholder, so a template, and here this will correspond to this T in the definition. And then on the right-hand side, you have a list of properties. And what you are saying is that the individuals which are built out of this template for these properties, for these individuals, these properties behave in a functional way. So for instance, this graph, for this individual which is built out of this template person, has only one age, only one car, only one name, and only one wife. Therefore, this is satisfied. But if I add another age, then this is not satisfied anymore. So I want just to give you an intuition what we are trying to do. So imagine that you have a Spark query where you try to join over the domain of this property. So you want to have all the name, the age, the car, and the wife for this person. Now, when you do the unfolding, this will translate into a join of SQL queries. And if you have this functionality, essentially you need also something more that I will tell later, then you can just replace this join with a query over one single table, essentially, or one single view. You can drop these joins. There is a second kind of virtual functional dependency, which is on the paths, of course, of properties. So this would capture this case. So you see that from person there is only one path, so there is only one list of nodes in this, such that you have a nationality, and then with the inverse of boarding, this minus means inverse here, I'm overloading the notation for semantic web somehow. You can you go back, there is indeed this thing, and there is only one person with this. But of course, this is not the case. Now, the main thing of the paper is about there is a relation between virtual functional dependencies and functional dependencies on the output relations for source queries in the basic mappings, where basic mappings are mappings where you only have one mapping for each predicate in the ontology. So you cannot have more mapping assertions than one for each element in the ontology. And you can reduce to this basic form. So the paper exploits these basic mappings, and I will present through these basic mappings, and then in the technical report there is the expansion for the general case. So if you add additional conditions, I will not go through the details, but I have an example later, then essentially this join, that would correspond to the join of the properties I was having before. Essentially all the answers will be the same, just of projecting over this the first SQL. This is a bit technical, but let's move to the example from the start of use case. So this is the ontology, at least a part of it. And here we have mappings. So let me just check. Okay, I'm going a bit too fast. So for the class Weber, we have one mapping here that selects all the Weber S, so this thing, and then there is a filter. So it's not just a projector over the table. And actually, this one is a view. It's not really a table. So this is a materialized view of some other query in the database. So these are what Webers are. And I also want to point out that also this property picks from the same view, and also completion date picks from the same. Now, data store statically has certain properties that derive from domain constraints and storage policies, which are, for this query that retrieves wherever. So when the mapping designer designed this mapping, he had in mind, okay, I give you this query because I want to return you all the elements of the class wherever. This is what more or less he had in mind. So when he's asked of the question, give me all the whereabouts, he will just give to the system this query. So, but of course, the OBDA system does not know this information, that this query is enough to retrieve all the whereabouts. Because the OBDA system, with respect to the ontology, if you look here, also production whereabouts are whereabouts, essentially because it's a development whereabouts, which is also a whereabouts, and therefore, when it does the unfolding, or the writing actually, it will just also look for all the production whereabouts and add them as a result of this query. So with exact mapping, you can say that this query is enough. So you specify this on top of the OBDA specification somehow. Another thing is that each whereabouts entry must contain about the information about name, date, and where. So there is no null essentially. And for each whereabouts, there is a single date where that is tagged as actual. So this looks like a virtual functional dependency, indeed it is. And this one is the additional condition that I was saying before. So essentially that you have this optimizing virtual functional dependency from the individuals built from this URI template for whereabouts to the properties completion date and ising well. And this is a branch in virtual functional dependency. Note that these properties are not specified as database integrity constraints, explicitly defined in the database. Why? Because these are properties over the result of a query, which is this one, actually I have it here. So these properties hold for this query, which is defined in the mapping, and actually also for this template. So it's not really something that you cannot in the database specify dependencies on top of queries. So this somehow goes beyond the optimization with respect to these integrity constraints that I talked about in the second or third slide actually. So let's have an example of what I was saying. I want all the whereabouts. So as I said, since production whereabouts is a whereabouts, I had to also retrieve all the production whereabouts. Where with SQL whereabouts here and SQL production whereabouts and SQL as interval, I mean this is the query in the mapping which is retrieving the whereabouts. And this is the one which is retrieving the production whereabouts. So essentially this SQL whereabouts is this query, okay, with this this projection. So you make the union. Of course, here I have to project only one because this was retrieving a tuple, not a single value. Okay, here this is just a technicality. This is just means that you attach the URI template to build the URI out of the database value. So this is not important. Now, since we had the exact mapping constraint, this query, we can remove these two unions because according to the exact mapping, these two unions are redundant, and therefore you can just replace this query as a query with SQL whereabouts, and you can still construct URI templates. Now let's enrich this query. So we have the whereabouts, and we want also to retrieve the information about the completion date and well of the whereabouts. So if you unfold, we will get the query that retrieves all the whereabouts, so this SQL1 that I presented in the previous slide, plus the query that retrieves the completion date, plus the query that retrieves the well. So, as I said before, this SQL1 can be simplified to SQL whereabouts. So this would mean that this join can become SQL whereabouts join SQL completion date SQL ising well. But if you remember the ontology, and I did not put an overlay here, so let's go back to the ontology actually. So to the mapping, sorry. completion date, and isInWhere, they're all picking from the same query, modulo the projection here somehow. Because you look for, in the table wherebore, with this filter, which is exactly the same filter here, and exactly the same table, and exactly the same filter, and exactly the same table. So this is really a trivial case of virtual function dependency, actually. So what we can do is just to replace this query as a projection of all the needed attributes. So this is why I put a star. I say replace this SQL wherebore with the projection list. You replace it with a select star so that you give out all the attributes, so also the information about the completion date and the where, not only the key for wherebore. So you do this, and then you still attach all the functions to build the URI templates, which is not important here. So let's see whether I can. I always get confused here. Here it is. So we repeated the experiments we did at Statoil by allowing on top to understand virtual function dependencies and exact mappings. So we added a component. And we ran our experiment with 15 optimizing virtual function dependencies and 4 exact mappings. These two things were found by a tool that we implemented that essentially was testing whether certain virtual function dependencies and exact mappings hold in the Statoil use case, essentially. This you can do because you have here in the information about the URI template, where, for instance, if you want to look for a functional dependency, if I have an example of virtual functional dependency like this, here you just enumerate over these URI templates, and then you check the condition whether this holds, essentially, over the given data instance. And so, but this, of course, then has to be validated by the database engineer, by the expert of storage. So these were found by the tool. Actually, not all of the virtual function dependencies, additional ones were added, actually. And then these are the improvements we found. So we had minus 74% of timeouts. The median time also improved of 57%. And we had an average number of unions of improvement of 65% and also of the join of 34% in numbers. So this was the number of queries that were timing out with the standard optimization, so this 17. With only the virtual function dependency, we got only 10 timeouts, and with exact mappings, only 11 timeouts. And when we use the combination, and the combination works better, as I said in this example, you see that in the example I gave in the slide before, I was using a combination, actually. We have only 4 timeouts. And here I have other statistics, like the average number of unions with standard optimization was 6.3, and then in the end you have just 2 unions for queries. So the queries sensibly become smaller. And the join as well. I want to point out, actually, that these queries are subset of these queries, because the result of folding is always a union of conjunctive query. So when I say the number of unions, it means that these queries were also in the original union of conjunctive query. And when I say the number of join, also the conjunctive query is just taking one conjunctive query from that union and reducing the join for that query. Which is why it makes sense to have the average SQL length here, otherwise it would not make any sense, actually. But this is not important. This is another just way of seeing the results, but it's the same information. Creative work. Now, in this e-box that Rosati introduced for DL Lite ontology, so this is another setting, it's not semantic web. He had a very, very similar idea because he also was imposing constraint, but the difference is that he was imposing constraint over the A-box. So the A-box will correspond to what I called here the virtual RDF graph in the first slide. So you impose constraint over the virtual RDF graph, and then you can improve your results. But this is defined and implemented for DL Lite ontology, so it was not applicable. We couldn't make any test with Statoil, unfortunately. Otherwise, it would have been actually very interesting, I think. The difference is that we impose constraints over the whole OBDA instance, so like mappings and the virtual relief graph. And the notion of perfect mapping is also related, but it's different because the perfect mapping is entailed by the specification. Instead, we declare a mapping to be exact, but you cannot entail it from the specification. When OBDA specification is the triple ontology, mappings, and database schema, essentially. So the take-home message is that here we have introduced two classes of constraints defined at the level of the OBDA specification, exact mappings and virtual functional dependencies, and that in this Tato use case they greatly help. But actually we have in the paper another use case with a synthetic benchmark made from the Wisconsin benchmark. If it's not in the paper, it's in the technical report. I think it's also in the, no, actually I think it's only in the technical report. Where there we also give a scalability analysis with respect to how many virtual functional dependencies you have and how much you shrink, and also with the perfect mapping we have a similar kind of analysis there. Yeah, so this allows OBDA to be applicable in contexts where otherwise it could not be applied, because the thing is that without constraints, you cannot get these shorter reformulations. This is the point. I mean, the OBDA system can never entail that all the wellbores are retrieved just by that query. That's the whole message, because simply it doesn't. I mean, from the logical point of view, you have the ontology, you have the database schema, and from those two things, you cannot entail that information. And I tell you now, is this really a limitation? Well, think of this use case. Imagine you have a database where you have persons, and then names and surname, let's say. And then you want to know whether names and surname they can be null as a columns. But in the database schema, they are not specified as not null columns. But you do know, I mean, this database is fed by a process, and that process actually is just a form where the name and the surname are mandatory fields. In that case, from the specification of the process, you know you can give to the OBDA system the information that actually name and surname are indeed never nulls, even though that information is not specified in the database. So I think that there can be done some research to automatize this if you put it in other formalism that take into account for processes. Okay, so this was the talk. Thank you very much for your attention. Good, it's finished. Any questions?
I have one. You talked about your benchmarks and empirical experiments. Do you also have some theoretical or ideas for theoretical analysis of the complexity of your work?
Of the complexity of my work?
Other theoretical.
Okay, well, the theoretical results in the paper are just that optimizing with respect to virtual function dependency exact mappings is correct.
Mm-hmm.
If you can do it with respect to this is the so then about the complexity. About the complexity, let me think about it. I mean, it depends on how you use them. I mean, in general, you can do many things. Like, for instance, with the perfect mapping, here we restrict it just to say we have the T mapping, so the saturation of the maps with respect to the ontology, and we just avoid from that. But essentially, an exact mapping, the definition, it could be also any other subset of the initial set of mappings. So in that case, yes, you would have an exponential analysis. But I mean, if you want to have a tool that finds whether a certain exact mapping is satisfied, or wants to enumerate all the satisfied exact mappings in an instance, that would be exponential. But for this tool, we just checked on the ones that were the difference between the T mappings and the original mappings, which is essentially the most naive, but also in practice it's the thing that one would do, because the additional complexity is given by the ontology actually. For virtual functional dependencies, well, a similar thing happens. Actually, I did not say, but for virtual functional dependency, the optimizing condition, it's connected to a containment condition. So query containment, which is undecidable, in this case, the containment is trivial because we were always speaking from the same table, if you remember. So essentially, we were removing just self-joins. You remember here, these were all these SQLs were essentially the same SQL. So the containment trivially holds. And this self-join is essentially the thing that happens most in practice, because when you translate from the database, where you have tuples, an n-ary model, and you go to RDF, which is only triples, then you really break down this n-ary tuple into triples, so that when you do the join, you really need to join many times over the same table to reconstruct the information that was in the tuple and that you lost with this representation of the RDF graph. So that case where you have all the same table is also implementing the tool. That's also kind of, you just go to the mappings polynomial at the end. But if you want to do the general case, then you should check the containment, and this is not even possible. So, or the user should tell you. So from the general point of view, I think virtual function dependency is even harder. Yes, probably it's not even possible with general SQL query. Yeah, it's not decidable query containment. But the point is, if you want to mine them automatically, of course. I'm not talking about, of course, if the user comes and tells you, like in this case, look, these are the things, like these are the exact mappings and these are the virtual functional dependencies, then you can just perform the optimization. And yeah, so this is.
Okay, thank you.
You're welcome.
Let's thank the speaker again. Talking about smart RL, complex sensitive ontology-based